All right. Now that I got you to stop talking and stop yelling at you. Inductive and deductive reasoning. Where was I? Oh yeah, detective. Who's read a detective novel? Yeah? So you understand they deduce things, right? So they use deductive reasoning. I think they use also inductive reasoning, but we'll talk about what the difference of these two things is. So first of all, let's talk about inductive reasoning. Okay? Here. Any guesses what this next one might look like?
8.
8? I'm going to divide it into 8 pieces.
So you have to read the other way.
Okay, so I would go, you think it's going to look like, so you're seeing a pattern 2, 4, 8 pieces. Okay, you think I go 6. So I think I see a few of you agreeing with that one. So I had 1 line, then 2 lines, then 3 lines. That wasn't a very good one, but well, who's right? We don't know. Okay. Both of you made an educated guess based on the pattern that you saw. Okay. That, and now if I gave you that and I said, okay, what's the next one look like?
16.
Okay, you know, right? For sure. This one, do you know what the next one's going to look like?
8.
Okay. So sometimes we have to see more in the pattern in order to make a really good educated guess. So on page 76, I hope you're there or can get there. This educated guess that you made, okay, is called a conjecture. So a conjecture is an unproven statement that's based on your observation. And that's where we're using inductive reasoning. We're looking at a pattern, okay, and we're making a conjecture about what's going to happen next. So a conjecture is an unproven statement that's based on observation. So we've talked about proving things a little bit. We've talked about what a theorem is. I showed you the vertical angle theorem a little bit. That's not inductive reasoning, okay? So there's no proof that that's the next one, or that's the next one, or that 16 is the next one. We're just basing our conjecture off of what we're seeing, okay? Now we learn that way really well. Okay, people learn by inductive reasoning a lot. In fact, I bet if there's someone here that plays baseball, you play softball. I bet if I throw this to you, watch her. Don't watch this fly through the air. Okay, don't. Okay, just watch her. So I threw it. Did you notice? I kind of threw it upward, didn't I? Okay. Well, did she throw her hands high in the air? Up above her head, even though that's where I threw it at first? No, she put her hands down low, didn't she? Throw it back to me. Okay? So when you were first a little kid, your dad or mother or brother or sister threw a baseball to you, or a football, or something like that. Right? And they threw it up in the air so it would get to you. And you put your hands up in the air, and what happened? The ball came down, hit you right in the face. Remember that? Raiden's like, I so remember that still.
I remember my little brother doing that with a rock and fence.
Oh, there you go. Okay. But after a while, you're like, hey, Someone throws something to me, they throw it up high in the air, but gravity affects it, right? And maybe you don't think gravity affects it, probably not. But it's going to come down and it's going to end up here. You know where it's going to end up, right? Okay? That's learning by seeing this pattern. We learn what's going to happen based on our observation of what's happened in the past. Okay? And I think as humans, we learn that way a lot. Okay? So that is called inductive reasoning. Look down at the bottom of the page. Okay? There's our 3 stars. You see the 3 stars? Okay? And each one of them is different, and there seems to be a progression going along. Any guess? How would it be different? Yeah, only one of the points of the star would be shaded, right? And then the next one would have no shaded ones, and then what about the next one? So after none are shaded, are they going to go all shaded at once, or do you think it would go, okay, 1 again and then 2 and then 3, or do we know for sure? No. Okay, but I think we can make a pretty good conjecture about the next one, can't we? Okay, so what about the little balls stacked up there? 1, then 3, then how many? 6. What are you going to add next? So sometimes I think we look at these pictures and that's all great, and you're like, okay, so the next one, I've got 3 there. Probably the next one we're going to add 4 across the bottom, aren't we? Okay. A lot of times, I don't know why, but I guess I'm a more number kind of guy, but I think I see that pattern. 1, then 3, then what? 6. So I see, oh, I'm adding 2, then I'm adding 3, and then what am I going to add? 4. 4, yeah. I'm going to add 4. And then I'm going to add 5. And then I'm going to add 6. And then add 7. And then add 8. So to get across the bottom here, you always end up adding 1 more than you had before. So there's a pattern. If you only see 2 things in a row, making a conjecture about that third one, did you notice we weren't maybe necessarily right as often? But if you see a pattern where you can see 3 in a row, you get a pretty good idea what that 4th one's going to be, don't you? Okay? All right. So, making and testing a conjecture. So here's example 2 at the top of the next page. A number such as 3, 4, and 5 are called consecutive integers. 3, 4, 5, 6, 7, 8, negative 5, negative, here, 3, 4, 5 consecutive integers. 8, 9, 10. Those are 3 consecutive integers. Negative 5. Negative what? 4. Nice. And then negative what? 3 are consecutive integers. So we're always going up the number line as we name the consecutive integers, aren't we? Okay? All right. So make and test a conjecture about the sum of any 3 consecutive integers. The sum. What does sum mean?
Add.
So if I take any 3 consecutive integers and add them together, can you make a conjecture about what that sum is, or a relationship with it, or I see a head shaking. Go ahead.
You can make it, because you can make an educated guess of what it could be.
Okay. And what could it be? Maybe if I hadn't have shown you that one, it would be easier.
What are you asking?
I'm asking you, if if I add those three together, or if I add these three together, or if I add any three consecutive integers together, what do you know about the sum? What do you know about that answer that you get when you add them together? Yeah, Kaisen?
No matter the combination of the three numbers, they will all equal the sum or some combination of the sum and one of the numbers
Yeah, if we add all three together, we do get the sum of them, right? Okay. Yes. But what do we know about that sum? Here, I'll give you one. I know the sum is greater than any of the three numbers we added up. Wait a minute. No, it's not. If these are three consecutive integers and we add them together, is the sum greater than any of the three previous? So I looked at some consecutive integers and I made a conjecture, right? I make this conjecture. The sum is always greater than any one of the individual ones I started with, right? But then I think about it. I start testing my conjecture. Is that true all the time? And then I think about these. These are three consecutive integers, aren't they? And if we add them together, -9, -12, that's not greater, right? But maybe instead of saying greater, maybe I could say the sum of the three consecutive integers is further from 0 than any of the three individual ones. That would be saying its absolute value is greater than any one of the three absolute values.
Could you say that the sum is the second number added?
The sum is the second number times 3? Ooh. What the heck? Is the sum here 3 times 4?
Hold up.
Is the sum here 3 times 9?
Yeah. Oh my
Okay, what about this one? Is the sum here 3 times -4?
Yeah.
Holy crap!
She's a witch.
Straight to that. Hey, yeah.
Hey guys.
Now, that is not what I saw. Okay? But, okay? That's true. Now, are we sure it's true? Well, we've looked at some cases, and it seems to be true, doesn't it? Okay? So by inductive reasoning, we think that that's true. That's our conjecture. Now you need to understand, that is an unproven statement. We could test a million, a billion, however many number you want, and show that that's the case. But as long as we're testing individual ones, we can't prove it's true unless we test every 3 consecutive integers, and we can never do that, can we? Okay? But, and this is a big but, we can prove it is true by deductive reasoning. Okay? And so let me show you. If the 3 integers, I'm just going to call the first one n. Would you be okay with that? I don't know what it is. It can be any integer. Positive, negative, 0 can be any integer. So it's n. Well, what's the second integer going to be? What's the next one going to be?
M.
Wouldn't it be n plus 1? And what would the next one be?
N plus 2.
N plus 2. And our conjecture is, if we take n and we add n plus 1, and then we add n plus 2, that the result is 3 times n plus 1. Isn't that our conjecture?
Yes.
Now, is it important that that's in parentheses? Absolutely, isn't it? So let's look at this side. Let's add our like terms. N plus n plus n, 3n, plus 1 plus 2. You starting to see it? What do you think? Let's factor a 3. So if we have a 3 in both of our terms, we can factor that. So 3 times n, that's 3n, plus 3 times what gives us 3? I don't know if you guys are used to factoring. I know you're used to the distributive property, aren't you? I guess I could have multiplied this one both by 3 and showed, but yeah. Okay, so this is deductive reasoning. Okay, whenever we prove something, whenever we have a theorem or something like that, then we prove it by deductive reasoning. Okay, but first of all, you have to come up with an idea. Okay, you have to come up with an idea. You have to look at a whole bunch of right triangles, and I'm talking a whole bunch, and you keep looking at them, and you're like, you know what? It doesn't matter how long I make these two sides. If I square that one and square that one and add them together, it's equal to the square of the hypotenuse. So I think, according to the 20,000 right triangles I've looked at and measured, that the sum of the square of the legs is equal to the square of the hypotenuse. I think that's true based on my inductive reasoning, based on my observation. That's my conjecture. Now, we need to now do deductive reasoning to prove that that's true. Okay? So that's the difference between inductive reasoning and deductive reasoning. But you have to do inductive reasoning first. You have to see a pattern, okay? And you have to make a conjecture about what that pattern's doing. And then you can say, okay, now is that really true? Can I know that for sure? Okay? Wait, say that louder.
Inductive is the idea and deductive is the reason.
I think so. I think so. I think without inductive reasoning, you'd never have anything to prove. You'd never be able to come up with an idea to think, well, is that true or not? Okay? Without deductive reasoning, you'd never know for sure if it was really true. You'd always just be hoping it were true. And there are some things that we have thought were true, and every time we test them, they're true. People have looked at it for 300 years, always looked true. But no one was able to prove it. Okay? No one was ever to actually come up with a theorem where they proved it by deductive reasoning. And then we got computers. And we started looking at larger and larger numbers and seeing, does this work? And all of a sudden, guess what happened?
It doesn't work.
It didn't work. We found one where it didn't work. We found one. Now later we found others. But as soon as we found one, what do we know? It's not true. Okay? And what is that one thing that we found? Remember, I said this yesterday. We were talking about where if our if-then statement was true or not. Did you have to come up with a bunch of examples, or how many did you have to come up with?
2.
Did we have to come up with 2 that showed it didn't work, or just 1?
I guess 1.
Yeah, I think 1. And what do we call that one example that shows it doesn't work?
Well,
Mm-hmm. So I used that word yesterday. I didn't ask you to remember it or anything, but a counterexample. Okay? So if we can show a counterexample, then we can say, okay, that doesn't work. Okay? Let's look down the page a little bit at example 3 on page 77. So to show that a conjecture is true, you have to show it works all the time for every case, which is hard. You have to do deductive reasoning. You have to make a theorem. Okay? But to show that it's false, all you have to do is come up with one counterexample. And that's one specific case where it doesn't work. So A student makes the following conjecture about the sum of two numbers. Find a counterexample to disprove the student's conjecture. Don't read on down below, just listen. The sum of two numbers is always more than the greater number. Well, let's see. 4 plus 7 is 11. Isn't that more than the greater of these two? 9 plus 2, that's 11. Isn't that greater than either of those two? So they're conjectures. The sum is always greater than the larger of the two numbers you add together. But I heard right away, Dempsey said no. All right. So what's our counterexample? Oh, okay. So he said any two numbers, right? So if we add a negative, -4 plus 6, that's 2. Okay. So we see here that the sum is not greater than the larger of the two numbers we're adding together, is it? Okay. So would that statement work if he would have said the sum of any two
Positive.
whole numbers or positive numbers, right? Or counting numbers? That would work, wouldn't it? But it doesn't work for integers. It doesn't for any negatives, does it? Okay. So that's how a counterexample works. Let's see. Okay, so think about this one now. Make and test a conjecture about the sign of the product of any three negative integers. Just think for a minute. You take any three negative integers, you find their product. You guys remember what product means, right? Okay, we'll find them together. Can you make a conjecture about the sign of that product? It's going to be negative. Agreed?
Yeah.
Okay, that's it. That's making a conjecture. Make and test a conjecture about the sum of any 5 consecutive integers. Wait a minute. The sum of any 5 consecutive integers.
We go like 1, 2, 3, 4, 5.
So 1, 2, 3, 4, 5. -3. -2, -1, 0, 1. If I take any 5 consecutive integers and I add them together, can I be sure about something about their sum?
They're gonna be larger than that.
So, like with the 3 one, where like, if you do the whatever the middle one times 3, you can do the middle one times 5.
What? So the sum of any 5 consecutive integers is equal to 5 times the third one in the series? Could we prove that the same way? Could we now go deductive reasoning, and could I show that works the same way we did with 3? You guys all agree with this? Guys?
It would only work with odd amounts of numbers though, because there wouldn't be a middle number for even amounts.
So right there, what he did was he thought about some examples, like, okay, if I took 4 of them, then would that work? If I took 6, would that work? If I took 2, would that work? And he made a conjecture about, oh, this is only going to work if you have an odd number. So if I had 7 of them added together, wouldn't it be 7 times the middle one?
Yeah.
But that's only going to, so his conjecture is that only works if you have an odd number, right?
But could we find in between the second and the third one?
Okay, so now you're thinking up another pattern. So if I have 4 of them, couldn't I go 4 times 3.5? So you guys are starting to see these patterns, right? And you're starting to make conjectures about what those patterns are doing, or seeing patterns within the pattern, right? So that we have to do that. Mathematics is the science of patterns. Have you ever heard that before? It's the science of patterns. We have to be able to look at patterns in the world, and then we have to make a conjecture about, okay, what's happening there? And then we have to use deductive reasoning in order to prove that that is really true, that we can trust it. Because I'm not getting on a rocket that's supposed to be going to the moon if someone can't prove a conjecture. Right? A lot of people have died because they weren't good at proving a conjecture. They could see something, they're like, birds have wings, they can fly. I'll make myself a set of wings that match my size, like a bird's, and boom, I can fly. How'd that work out? That work out for everybody?
It'll do the same thing as a penguin, because penguins have like wings and they can't.
But they have
fly.
tiny.
Also just
But
can't
penguins
fly
have
either.
tiny wings.
What about ducks?
Ducks can fly.
Okay, that's very good, everyone. That's not the point. Is
They migrate. Not all domestic.
if you come up with a conjecture that you're going to base risking your life on, right? You want to be able to prove that it's true. Okay? All right, now we're going to talk about deductive reasoning a little bit more in detail on Monday, but that's enough of inductive today.